Yo, what's up, guys? Welcome back. Episode 44, I think. 45, maybe. But yeah. Been a long day today, for sure, but we're gonna get a couple problems in today. Potentially there'll be a lot of snow tomorrow, so that's kind of crazy. Kind of like it when there's a lot of snow. It's pretty fun. Looks kind of cool. But yeah, let's get straight into it and check out our new Pokemon of the day. Oh, it must be episode 45. Actually, we got a Vileplume. Pokemon sound. Shall we check out the sound? Check out the sound, shall we? Oh, jeez. Oh, man, it's gone, like, around my headset. Is that even a sound? Sounds like somebody's come out of, like, a bush or something. Interesting. Anyway, we're gonna get straight into it. We'll check out our problem of the day. Because why not? Might as well check it out. That's my eyes, man. Jeez. Remove all occurrences of a substring. Given two strings, S and part. Perform the following operation on S until all occurrences of substring part are removed. Find the leftmost occurrence of substring part and remove it from S. Return S after removing all occurrences of part. What we gotta think here? What would be the best way to solve this problem? Originally, my first kind of thought process to this problem was to use a sliding window. But I'm trying to think. I don't know. See, the thing is, I don't know if a sliding window will work because technically we'll have to reset the window every time, right? It's because we see this, we remove these values, and we reset the window. We see this, we remove these values, we reset the window. You know, so I don't know. Let's check out a hint. Note that a new occurrence of a pattern can appear if you remove an old one, for example. Okay, well, yeah, I knew that. Maintain a stack of characters, and if the last character of the pattern size in the stack match the pattern, remove it. So it's a stack problem. I kind of thought more of a sliding window. But why is it stack? Let's take a look. Why is it stack? How would we use a stack to solve this problem? It does have a pretty good solve rate, except it's for 80%, so it must not be too difficult, but it's just the idea of doing this isn't coming to my head. I'm trying to think. If we add each value, right? Only comparing to the top of the stack. So I guess maybe we can keep adding, right? Until we see the first value in the string. Maybe? Let's see if that works. that could be it. So we have our string D A B C B A B C B C. Okay, right? So we have our string here. Whoops. We have our stack, right? We add D, we loop through and we add D. We loop through, we keep looping through, right? Until we see the start of the stack, right? I mean the start of the part that we want to remove, right? So we see A, right? Then we increase this pointer to B, right? In this case we saw A, right? So we put A here. Then we increase our pointer to B, right? So we put that on the stack. Then we compare the top of our stack to the next value, right? So is A equal to this part of the stack? If it's not, then we just add A to the stack and we reset our pointer here back to A, right? Well, technically, we need two different conditions. We'd have to either reset our pointer back to 1 or reset it to at 2. That's what I'm kind of thinking. You know what I mean? So in this case, we had we had an extra A, right? So technically we're at 1 again, right? Or I guess we can just reset to 1 every single time. I mean, technically, right? Because we can keep checking. But anyway, the point is that we do this checking, right? Until we see an A. Okay, so this works. So then, okay, we're moving back to B, right? So our pointer is a B now. Then we see it's B. We add B, and we increase it to 2, right? So then we're at C. If C is equal to the last character here, we don't even have to add C to the stack. We just pop the next 2 elements, right? Which means we've done all these, right? And then we keep adding, we go B. Do you know what I mean? And then we go all the way through. No, that actually won't work, I don't think. Let's check out the discussion. Is it hard or am I getting dumb? Seems like it's a lot more simpler than that. I'm not sure, man. Okay, so let's get a hint. Okay. Charnes, right? I guess when we just add a value to the stack, let's do window is equal to list part, right? I'm gonna go back and think about it the way that I did it, right? Like, or the way I was thinking about it, right? Value in S, we can check. Well, if yes, we can replace that, make a count variable, right, to access our indices here. All right, count is equal to 0. If window if the first element of window not equal value, right? And we just append to our stack, right? This is our basic thing. If window count does not equal value, then we just append to the stack, right? So if it doesn't equal our count, we append to our value and we make count equal to 0, right? It's technically it doesn't, right? And then technically else if window count is equal to value, then we can append to our stack and increase our count, right? And we can increase plus or equal to 1. Else if window count is equal to parents as well. Maybe not a 4, maybe we need a while. Maybe a while loop would be better. We could do while maybe a while loop would be better, right? So we could do while I is equal to the length of S, right? While the length of S is greater than 0, right? Sorry, while I is greater than 0, you can use I to access does not equal value. Sorry, if window count does not equal sorry, I guess I is equal to 0. And we start I at 0. I is While I equal to the length of S, right? Then if window I does not equal value, then we stack.append it's not equal SI and stack.append. Count is equal to 0. Else if I is equal to SI. Do stack.append. Then we can do count just equal 1. Alright, we increase our count. If count is equal to the length of S minus 1, right, we've found our window. Technically, it'll keep going until, well, we'll get 1 in this case. 1, 2, 3, right? Then we gotta drop it. So we're gonna make count is equal to 0. we got to pop here again. So we got to do for all count does not equal 0. Stack.plot count minus equal 1. Right, then we go to, or wrong, we go to 0. We go to 0. And then we'd reset I to 0. Set I to 0. I is equal to 0. Then you just want to, I guess, return, what are we returning here? String. So, stack. There's no shot this works, but there's going to be something wrong here. I don't think this is an efficient way to use a stack, to be completely honest, but oh yeah, the index is out of bounds. Jeez, it's meant to be count. No count. Let's be count here. match part. Length stack is greater than part length, and dot join stack part length equal to part. Delete stack part length. Bro, if I knew that this was possible, like, bro, what? Alright, this seems like it's fucking. Oh my gosh, dude. Like, bro, like. Here's what I do. They create a stack, then they're getting the length of the part, right? The target end char part minus 1, right? I mean, it's just unnecessary, but alright. The current char in char result.stack.append current char. If current char is equal to target end char, and the length of the stack is greater than or equal to the target length, if dot join result stack is equal to part delete result stack. I didn't know you could delete, like, what, 3 in this case here, 3 things from the stack, bro. Like, what? That's not even a freaking stack at that point. Like, just like delete like that from the stack, dude. Like, what? How do they do it in Java? Bro, it's cheating, dude. This is so stupid. Okay, whatever. Okay. I can get rid of this. I can get rid of this. Okay. So, char and s, right? Stack to the pen char, right? Yeah. Okay. So now we want to check. Well, the length of the stack is greater than or equal to if the length of the stack, the length of string, the length of s, sorry, and no, sorry, not the length of s. We want the length of part is greater than or equal to window. And okay, the length of stack is greater than or equal to window, and what was the other thing? If current char is equal to target end char. Yes, we can do. We can slice, right? Join stack part underscore length underscore length stack. Stack part underscore length. Yeah, bro. Yeah. Ciao. Do we even need this, bro? I don't even think we need it. This would be window, and this would be window. Oh, we're not even comparing, bro. It's equal to part. Only join if can only join an iterable. What is wrong here? There we go. Oh, bro. What is the fastest way here? Bro, what is this? While one, if part in S is equal to S dot replace part one, else break. For what? What kind of goated solution is this, bro? Jesus. Bro, I didn't even think this would... Like, bro. I didn't know while loop does that. If part and s to replace part. How does the replace function work in Python? I've never... And it keeps returning 1. Also breaks. Interesting way to think about that. That was an interesting problem. Definitely want to keep this solution. I'm going to submit it. Just to save it to my Git. I want this to push to my Git. Yeah. It's such an interesting way to think about it, you know, like I feel kind of like an idiot that I couldn't solve that, to be honest, but you know what happens, it happens, bro. Predefined methods are very handy. Like, bro, even this, I feel like this is cheating a little bit, you know, like slicing in Python, like, bro, like, I don't know. I'm curious. I'm actually going to look at it. Let's check out a Java solution or something. Let's check out a Java one. I mean, I guess it's the same one, actually. Let's go to Java. Interesting. Alright. Cool, bro. Cool. Oh, man. Jeez. Let's do a binary tree problem. This looks like a difficult problem, honestly. Like, but we'll try it. We'll try it. Given the root of a binary tree, the depth of each node is the shortest distance to the root. Return the smallest subtree such that it contains all the deepest nodes in the original tree. The node is called the deepest if it has the largest depth possible among any node in the entire tree. The subtree of a node is a tree consisting of that node plus a set of all the descendants in that node. Yeah, that's what I was thinking too. Like, or at least want to. I don't know. Like, a single leaf can be a subtree. Yeah, to be honest. Let's check out this one. Maybe the description's better. Like, is a leaf if and only if it has no children. Okay. The depth of the root of the tree is 0. If the depth of the node is d, then the depth of each of its children is d plus 1. The lowest common ancestor of a set S of nodes is node A with the largest depth, such that every node S in the subtree. Depth of the root of the tree is 0. Alright, bro. The depth of the roof of tree is 0. If the depth of a node is d, the depth of it. I'm still kind of confused on the question. Do a post-order traversal. To be completely honest, I think this problem is a little bit too out of my comfort zone right now. Let's take a look at this one. Post-order traversal. Because I'm actually not really 100% sure what a post-order traversal is. I'm kind of confused. Like, 1, 2, 3, 3, 2, 1. So is it just like post-order traversal? I don't even know what that is. What is a post-order? Post-order traversal is a depth-first search algorithm for a binary search tree that first traverses the left subtree, then the right subtree, then the root. Okay. So we traverse left, there's nothing left. So we traverse right, so we go what, 2, 3, 1? Three, two, one. I'm so confused. So we return 4. Oh, okay. I think I understand. I think it's 4, 6, 7, 5, 2, 9, 8, 3, 1. Yeah. So we're going all the way left. So we have to go left, left, left. And then the rest of the nodes. Okay. I think I understand. Okay. How would we do this? What are we returning? A tree node? Oh, returning a list, sorry, okay. Returning a list, right? So let's get our list. We want to create a while post order traversal. There's def DFS. Our base case, right? But what is our base case here? I generally don't know what our base case is. What would be our base case? We don't know what would be our base case. I generally don't know. What would be our base case in this case? One. We want def DFS. We want to pass in our node and our res array, right? I guess somehow we got a loop left and keep looping. Can you do this? Okay, we want to recursively visit the left tree, recursively visit the right tree, process the root. So the root node is always last, I think. Right? 1. So the root node is always last. If not node, return, right? This case is if we see a null node, right? If we see a null, right? Because technically we just want to continue if we see a null node, right? Left, then we return well. Do DFS, node dot left. That's node dot right. I don't think we need to pass in the res every time, right? I mean, we just need to append to the res. I think this is how it works. So I think if we call this method constantly, so come out here and we call DFS root. No. Result dot append dot val, right? Firstly, well, I think we want to calculate no dot left, right? Geforce no dot right. No. I don't know. Oh, I think we only need a root. Return res. Oh, there we go. Okay, so I think what this is doing is that we're going for the root here, right? So we're doing the root, then we're appending the left, right? We run through this node, we see that, okay, now then we go left, right? Boom, left. Right, so I think we just keep instantly calling no dot left, and it just keeps going, like, no dot left, right? And then it goes no dot left and sees it's null, then it goes back to this one, right? There it goes. Right? So I think it goes, hang on, I think it goes no dot left, no dot left, no dot left, sees it's null. If not no, return. So it returns. Then it goes no dot no dot right is null, returns. Right, goes back. No dot right, and then since we go no dot right here, it goes no dot left, then no dot left is null, comes back, no dot right is null, comes back, goes back here, sorry, then it appends, I guess, goes back here, no dot right, no dot left, no dot right, and then comes back, comes back, comes back, no dot right. Here, no dot left, sees it's null. Right, then goes no dot right, no dot left. Comes back, no dot right, comes back, appends a value, appends a value, appends a value. Okay, let's do this in a stack, right? Okay, right, so if we were to do this using stack, here we go. Stack is equal to this, and we just want to put it in our node, right? Just put in our root here, right? So while stack, then we do this is equal to stack.pop, right? And we loop through, we go, well, no, we don't want to pop though. I don't think we want to pop here. I don't think we want to pop here. We want to do. Jeez, bro. How can we visualize this on a stack? I guess we'd only want to, if no dot left and no dot left and no dot right, and I think we'd want to pop from the stack, right? Then we'd obviously res is equal to stack dot pop. Let's do resi is equal to stack dot pop, and then we do res dot append resi dot val. Else if it's not, how will we know here in this case? If no dot left and no dot right, no dot left. Alright, so we come here. We have our stack, right? We have our res, right? We want to output 4. How can we get 4 from here to be appended? Well, we'd have to. I guess we do well if node dot left, then stack dot append node dot left. Else if node dot right, we always check node dot left first, right? I don't know, dude. I don't know. It's kind of close. I mean, we get the stack root here while stack, we pop, right? Output underscore stack dot append node. Push left and right children in reverse order. Oh, I didn't think about it like that. Shit. Stack, right? While stack dot pop. But why are we appending our res dot append node here? I don't understand why we're appending so quick. Do we reverse? Ah, we reverse at the end. Okay. We append our node here. That's why, because we're going to reverse. We push left and right children in reverse order, right first, to ensure the post order. Stack dot append, node dot right, node dot left, stack dot append, node dot left. And obviously we want to build our result. Result is equal to node dot val in res. Sorry, for node in res. Node in reversed. Sorry, my bad. Reversed res. Return result. I think what's wrong here is that these need to be flipped. default val. I guess we can just do res. If not root stack, res while stack node is equal to stacks up above, res dot right, node dot left. I think it's this. I think this needs to be swapped. Why do we append left first though if we're reversing? Take a look at this. So if we got one null, two, let's get a better one than this, man. It's too long. Bro. Give me something simple, man. Okay, right. Let's just. I'm gonna put it over here. Let's copy this one, right? So we got our stack, right? Okay. Got our stack, right? If not root stack, res while stack node is equal to stack dot pop. So we do. Okay, we start on our root. We start with the root node, right? Which is 1, right? Then we pop from our stack. Right, we pop. We add res to the root, right? So we add, let's go down here, right? We add 1. And if node dot left, we add 2, right? So we do 2 to the stack, and then we add node dot right. So we add 3, right? And we go while stack. And we pop, right? Oh, but we're already reversing. We pop, right? So then we pop 3, 2, boom, boom, boom. Oh, sorry, wait, hang on. So wait, we add 3, 1, 2, right? So we pop this one. We pop 3 from the stack, right? Then we check, well, if left, no, then if right, then we put 8, right? So then we're at 8. And we pop 8 from the stack, right? And we check no dot left, well, no dot left is 9. So we put here, there's no right, so we don't put anything there, right? And we pop 9 from the stack. We see that there's nothing there, so we're done with this side, right? We popped all this stuff, right? So then we go to 2, right? So then we pop 2 from the stack. We see that we got a 4, so we add 4, and we add 5, right, on our stack here. Then we pop 5, we see that there's a 6, so we add the 6, and then we add the 7, Alright, then we pop from 7, we see there's nothing there, so we leave it. Oh man. There's nothing there, we leave it. 7. So then we check 6, there's nothing there, so we leave it. I guess we're gonna have to go through this all over again because I didn't even add to the stack. Whoops. Okay, let's go here. So we had 1, we popped 1, right? We had 2, right? We had 2, then we had 3, right? We had the children. We're at 3, we pop from the stack, right? Then we add 3 over here. Pop from the stack, add 3. 3 we check left, there's nothing left. Then we add 8, right? Add 8, we pop 8 from the stack. Add 8 over here. We add 9, but there's no right. So then we pop 9 from the stack. So then we add 9 here. See, there's nothing. So then we go back to 2, right? So now we're at 2. See, node dot left is 4, node dot right is 5. Okay. Right. So then we pop here. We add 5 here. 5 has 6 and 7, so then we add 6 and 7. Right. We pop 7 from the stack. So then we add we add 7. Right. There's none. So we check 6. There's none again. So we can pop 6 as well. Then we go back up to where we are in the stack. We were at 4, right? Then we see there's nothing there. So then we add 4, right? Then we reverse this, right? So then we return 4, 6, 7, 5, 8. What is this? Do I have 2 8s, bro? What? 4, 6, 7. Is it 2? Bro, I don't even know. 4, 6, 7, 5, 8. Maybe it's a 2. This must be 1, 3. Alright, we forgot to add 2, but this is right, yeah, because we're meant to have 1, 3, 9, 1, 3, 8. This is meant to be a 9 here. 1, 3, 8, 9. Then we're meant to have 2 here that we forgot to add. 2, whoops. 5, 7, 6, 4, yeah. 4, 6, 7, 5. 5, 2, 9, 8, 3, 1. Okay, you guys can see my terrible drawing here, but this is exactly what I'm meant to return. So in a way, this question, you have to think about reversing it backwards, but the stack is kind of like looking at it in that order anyway, I guess, technically, because technically, I mean, in a normal DFS, right, we're looking at it from left to right. So we're going 1, 2, 4, 5, 6, 7, right? And go back here, 3, 8, 9. At least I think. I think that's what DFS is. Yeah, I think that's. I'm pretty confident that's DFS because depth first search, so you go depth. Was DFS? Oh my gosh, dude. I always go right to left. Man, I'm so bad. In typical DFS, you go from left to right. Okay. Pre-order DFS works by visiting the current node and successfully moving to the left until a leaf is reached. Okay, let's check. Well, between DFS, post-order traversal, and pre-order traversal. Curious. Pre-order traversal, root, left, right. Okay, yeah. So I was right. Okay, so DFS is pre-order traversal. This is post-order traversal though, right? So pre-order traversal goes from we start at the root and we go left and then right. You start with the left side of the tree. Hit the root first, recursively traverse the left subtree, recursively traverse the right tree. Yes, we go left. Right, we look at all these, come all the way back, then right. BFS goes by level, I think. BFS. Level by level. Yeah, starting point. Uses a queue to keep track of the nodes to visit. The queue operates on a first in and first out FIFO basis, meaning nodes are processed in the order they are added to the queue. All nodes at the current level are processed first, i.e. all nodes currently in the queue visitor. Yeah, so BFS goes by level. Okay. Okay. That was an interesting problem. We'll come back to that though. It's a binary tree post-order traversal. My friend's in Discord. Maybe he wants to join us on a problem. Let's check it out. Hello?
Oh shit, what's up, dude?
Dude, I'm in the middle of recording a video, bro.
I get like a shout out?
Dude, yeah, you're in the video now, bro.
Dude, let's go. What's your Pokemon of the day, bro?
He was, shit. I think a V-Loom or something? What was it? I can't even remember. The evolution of...
You need more energy when you copy the calls, man. Yesterday was weak.
Yeah, bro, I get tired sometimes, man. But, it's, Viplume, dude. Viplume. The evolution of Gloom. Wait, sorry, what were you saying? I have, like, no energy in the videos?
No. Like, when you, like, copied the battle cry, it was so weak, man. I was like, waiting for it. It was so weak. I want energy, bro. What am I watching you for?
Okay.
I'm strolling.
Okay.
I gotta go in like 50 minutes though. I gotta practice.
Oh shit. Okay. Let me look at one more problem. It should take me like hopefully 10 minutes. Let's take a look. Do you want to like get the live action going here?
Oh
yeah, bro.
God,
I'll share my screen, bro. Alright. Okay, so we're gonna look at let's look at a hash table problem. Oop. We'll do an easy problem so it goes quick. Find common characters. Let's take a look at this one. Given a string array of words, return an array of all characters that show up in all strings within words, including duplicates. You may return an answer in any order. Okay. String array of words, return any... God, I'm getting text, bro. Hang on 1 second. Return an array of all characters that show up in all strings. All characters that show up in all strings within words. Oh, so is it the letters that are in all of them?
Yeah.
So it shows.
Because like in the example 2, there are 2 Ks, but not in all, you know.
Yeah. Okay. Alright, so return an array of all characters that show up in all strings within words. Okay. Okay. So what I'm thinking is that we use, I think, a set here. We add all of these. Hang on. Let me take my fucking push to talk off, dude. Fuck me. Hang on. How do we check? Oh my god, dude. How do I turn this push to talk off, dude? Do you know how to turn off push to talk, Rohan, in Discord? I don't even know.
Yeah.
Where do you go?
Yeah, it's in settings. It's in settings. It's in audio or mic or whatever it is.
So I click the user settings down the bottom left, or the...
Yeah, user setting.
And then you go to, oh yeah, voice and audio, okay.
Like mic or audio, and then
There we
there'll be
go.
like a slider.
Okay, you can hear me now, right? Okay.
Yeah.
Sweet. No. Okay, so...
Is your push to talk still control?
Yeah.
Just doesn't say.
Yeah, it is, bro. Okay. Oh, wait, hang on. Let's do I in range length words. If I in hashy, and let's create a res array here. So if I is in hashy, we want to res dot append words I. Wait, oh shit. How to put a I think this is only gonna loop. Hang on. I wanna see how this loops really quick. Oh, whoops. Was I? Oh. Oh, I hate this shit on Leetcode, dude. Oh my god. Okay, we need to combine this into one array. How do we combine this into one array? Okay, let's do line list is equal to this list. List of dot join words. Print line list. Okay, sweet. Okay. So we got that. So we have a hashy. So now if hashy, if for I in line list, I in hashy, and we want to create a result array here to return. I in hashy res dot append I guess then that's it. Print, just print out res. What are we getting here? We're getting a null. Why are we getting null? Define hashy. Oh, we're not appending anything. add I. Are we still outputting nothing? And combine this hashy dot add I if I in hashy. Bro, why am I outputting nothing, dude? What is going on here? Oh my god, I'm not returning anything, that's why. Jeez, return res, that's why. Oh my gosh. I'm so stupid, dude. I'm not returning anything. Output. Shut if I and hashy. Bro, why is it appending everything? I'm so confused. P. Bro, I don't understand why this is appending everything. Like, what the fuck, dude? Roller. Alright, just like a combined list. Hashy dot add. I wonder if this will change the name. Combined list. I. If combine list I and hashy. I don't think this should do anything in theory, but Bro, what the hell? ELL. Why is this not working, bro? What the fuck, man?
Bro, this is an easy question.
I don't know, I'm not even getting it, dude. I'm so cooked, bro. Why isn't this appending? So pretty much my thought process here, right, is that we have a hash set, right? And a hash set you can't hold duplicate values, and we're looking for duplicate values, right? Oh, sorry, you may return an array of all characters that show up in all strings within words, including duplicates. You may return the answer in any order. So here, pretty much we're returning this array, we're returning duplicate values, right? That we can see in both of the things, right? So what I did here is I combined the list, and I made it all one list so we can iterate over each thing in the list, right? We're adding each element into the list, and then we're checking, well, if this element in the list is inside hashy, and we're adding it in every single time, technically, if it is in the hashy, then we'll notice that it's a duplicate value. Oh, that's why. Hang on. Wait. No, that should still be fine. Wait, hang on. I'm tripping balls. We're adding each element to the hashy, and then we're checking, well, if the combined list is in the hashy, right? Dude, what the hell? Combined list is in the hashy, but we're appending value. Yeah, that's what we're doing. Bro, why isn't this appending? Bro, I don't understand why this isn't working. I've obviously done something wrong, but I just don't know what it is. Combine list and hashy. Res.append. Combine.
Do you have to tab the if, or will it work fine?
No, it's fine with that. I don't understand why this isn't returning values. Why is this not returning? Why is this? Yeah, because a set is like a special data structure that can't hold duplicates.
Duplicate, yeah.
Okay, I'm gonna think of this in a different way. If okay, char in blind list, char not in hashy. So it's not in the hashy, then we just add the value. Hashy dot add char. Else, if it is, then we add hashy dot, res dot append char. Return our char. Sorry, return now res. Okay, we're getting a different answer now. We're doing something wrong. Given a string of words, return an array of all the characters that show up in all strings within words. Oh. Wait, return an array of all characters. Oh, that's why it's wrong, bro. Wait, hang on. Return res. Oh my gosh, dude. I'm actually getting kind of triggered. I'm not getting this, bro. Low-key, bro. Like, what the fuck? I feel like such an idiot right now, bro. Get a string of words. Return an array of all characters that show up in all strings within words. So we're looking for each character that shows up in each of these words. So obviously B wouldn't work. We'd want E. And we see L. We got L in these ones. And then A wouldn't work, right? So yeah, E, L, L. Oh wait, we're putting in L.
Because all three of them have two L's.
Ah, okay. All three of them have two L's. Yeah. Okay. Okay, I think we have to do this a different way. I thought we were just getting duplicates in each character, but since we have many different words to work with, then do you have any idea, bro? Low-key?
Dude, I have zero clue. That's what I'm saying, dude. Dude, I don't even know what res append is.
We're just like appending the value to the array. I'm trying to think. I think now that I put it all in this, I don't think it'll work combining it all. Because then we're not keeping track of each value. Like here right now, we're just appending the duplicates, right? In this list, right? We're just appending duplicate variables. So here we'd append B. You know, that's why B is in here. Because we see B twice. B's here, right? We put this all in one thing, but I'm thinking we have to... Oh. Is our word always the same length? I don't know. Dude, this is so interesting. I'm kind of bamboozled right now a little bit, bro. Bamboozled, dude. Like... a little bamboozled, bro.
Bro, if this is an easy question, like, how long does it take you to solve a hard question?
Bro, I've only ever solved like 2 hard or 3 hard questions before, and they're probably like the easiest hard question on the website. Usually the easy problems I get in like 5 minutes, bro. Honestly, like 5-10 minutes, I usually can do an easy problem, and like mediums like usually take like me like, bro, like anywhere. It could be anywhere from fucking like 10 minutes to like an hour and a half. It just depends on the problem. And like it depends on things. Like usually problems like this, actually, bro. Like looking at this topic. Like, these are usually my best ones, where I work with hash tables and arrays and stuff. They're, like, the easiest ones for me, but I can't seem to get this one. But I think now I think of it in a different way, is that I think what we have to do here is that we have to compare each word. So it's like, if we... So we, for example, we could iterate through this first word, right? We iterate through each value. Hang on, I think this is the better way to do it. Hang on. So I originally thought we combined the whole array, right? So, like... BELLALALABELROLLER, right? So I thought we combined the whole thing, just did the values. So we're taking in the duplicate values here, right? But instead, I think we...
Just compare each word to each other.
Yeah, so we work with the first word, right? And we put this into a set, right? Or put this into a set, just this word. So we have B... So we have this in here in the set, right? And then we go over each other word in the array. So then we go through label. And then we compare, well, is L in this one? No, that wouldn't work. I was thinking, well, if L is in this one, then it is. Then we can put it in our set, right? But then again, it wouldn't work because then we have multiple different words. So now I'm thinking... Usually easier problems are easier than this one too, bro. This is actually like, I don't know, this is kind of bamboozling me a little bit. Let's check the discussions, bro, low key. See what people say. How bloody hell is this considered easy, especially when there are easy problems where the solution is literally one check and a counter. This is the hardest easy problem that I've ever done.
Bro, you're not the only one, man.
Man, bro, this one's bamboozling me, bro.
It's bamboozling everyone.
Okay, maybe here. Okay, maybe we create a dictionary. Okay. Okay. So a dictionary holds like key value pairs, right? So when you think of a dictionary is kind of like it's like a data structure that holds a key and a value, right? So like a key could be like dog, right? And let's say that we hold 5 dogs. There's a cat, we can hold like 70 cats. If there's a bird, we can hold 19, right? So like when we're using the key, we're referencing this as like kind of like the value in our thing and the count, right? And what I'm thinking here is that maybe we could go through each of these right? Maybe we could take the length of this array, right? The length of this array would be 3, right? So that means for there to be a duplicate of the value here, then in our case, hang on, let's get rid of all this, right? Let's get rid of this. So we take the length of words, right? So the length of words is 3, right? Then we loop through our list, right? And put B-E-L-L-A, so that like we do the same thing we did before. We combine the list, right? And we hold a key value pair for each value here, right? So we have B, we have E, L, A, right? That's Bella there, right? In this case, our key value pairs for this test case would be B maybe is, and this whole thing is 2, right? Because we've got a B here and a B here. We have an E here, an E here, and an E here, so that's 3. The amount of L's we have is L, 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 L. Yeah, 6. But I don't know if that would work either, maybe. That's pretty much, so I was thinking is that we could hold each key value pair, right? And if it was 3, well, we could return it because then we know we have 3 words and 3 values, so that means to be 1 in each. But then again, for each different word, maybe one word could have 3 L's and the other ones don't, so that doesn't work either. I don't.
You stomped, man. Alright, dude. I need to go to practice right now.
Alright, bro. I'll see you later, man. Chat, have we been doing this for 40 minutes already, dude? What the fuck?
Alright, see ya.
Alright, see you, bro. Okay, we're going to get the frequency count of the first word. Honestly, I'm kind of stumbled on this one. I'm not really too sure how to approach this. I honestly don't know how to approach this problem, bro. What the hell did I just do, bro? Bro, no way. What did I just do? Give me the default layout. Oh, man. What? Okay. I honestly don't know. Yeah, you know, I'm not really too sure. Is there any like hints or anything? Initialize baseline frequency. Create a frequency map for characters in the first word. This map will store each character and how many times it appears in the first word. Process each word. For each subsequent word, create a temporary frequency map to count the characters in the current. Create a frequency map. For I in words, right? I don't know. Bro, this is frustrating. There must be a Leetcode on this one, bro. It has to be. 1002. Leetcode 1002.
Hey everyone, welcome back. Let's take some more Leetcode today. So today let's solve the problem. Find common characters. We're given a string, or basically a list of words. And so the way this is worded is honestly kind of confusing to me, but let's break it down. We're going to return an array in just me. The idea is basically just look at the example, don't even bother with the description half the time. Common to all three strings. It looks to me every single one of those words has an E in it, and every word has, there are duplicates in here, highly suggests the fact that for every given word, let's at least count the occurrences of every single character. So let's do Bella. Looks like we have a single B. Looks like we have a single E. We have two L's. I'm not really sure how to make this look not like a 1, but, and we have a single A. We can do that for the other two words. I'll just kind of fast forward that. So we counted the words. Now, let's just go through every single character. B. It looks like it's in these two words, but not this one. So we can't include that in the result. What about E? It does look like it's in all three strings, and it has a count of 1. Suppose this one, for some reason, had 2 E's in it. What would we do? Well, we'd say this one has 1 E, this one has 1 E, this one has 1 E. It technically has 2, but we have to take the minimum, right? We have to take the intersection of these three and then minimize it. So we'd say we can only have 1 E. In this case, though, this one already has 1 E anyway, so it makes our life easy. So we just put an E down here. Next, we look at L. It's in all three of these. So the count of it, again, is 2. We take the minimum, and it's 2 in all of them, so we would take 2. If suppose one of these only had 1 L, then we'd have to take the intersection. These have 2 L's, but this one only has a single one, so we'd have to put 1 L. But that's not the case. Each of them has 2, so we can put 2 L's in the output. Last, A has a count of 1 in these two words, but it doesn't show up in this word. Now you might think, well, don't we also have to look at some of the other characters? Like we only looked at B, E, L, A. We did not look at R, nor did we look at O. But my claim to you is we actually don't need to look at the keys of every single word, because we only care about the keys that show up in every single word anyway. So it doesn't matter whether we iterate over the keys in this word or we iterate over the keys in this one or this one. We just have to pick a single word and then check which of those keys belong to every single word. The answer will be the same. Like in this word, we see that E and L show up in the other words as well. R doesn't, O doesn't either. So now this solution does work. This is a perfectly valid solution. Just count the occurrences for every single word, then just pick one word arbitrarily, go through the keys of it, check does that key exist in all the other words, and then minimize the count. This works. It's kind of complicated to code up, and also if you think about the space complexity, every single word will, like an individual word, will only have up to 26 distinct characters, lowercase a through z, I think. But the number of hash maps we're going to create, each one of them is going to be constant size. That's what I'm getting at with this. But the number of hash maps we're going to have to create is going to be proportional to the number of words in the input. Let's say that's n. So the overall space complexity is going to be big O of n. We can actually reduce the space complexity to 1. And I'm going to show you how that is. We're going to take, let's say, one of the words, this one, and then we're going to build a hash map with it. So this is constant space so far. Once we have that hash map, we're going to say, okay, this is the most amount of characters that could possibly be in the output. Like we can never have more than a single E in the output, because if this word doesn't have multiple E's, it doesn't matter how many E's the other words have, because we have to minimize the count. So, okay, so this is at most the number that we could have in the result. Now we're going to count a second word. Let's pick this one just to make it more interesting. So we have these two hash maps in memory. This is still constant space. Having two hash maps that are of constant size is still constant. Now what we're going to say is find the intersection of just these two. Before we were finding the intersection of all the hash maps at once, but now we're going to do it pairwise. We're just going to look at two hash maps at a time. And so I'm going to pick this one to iterate over. Let's check. B, is that common to both of them? No. So what I'm going to say is, screw this. B is never going to be in the output because we found at least one word that does not have B. Okay, let's try E. Okay, it does show up in both and the count is the same. So let's keep this. What about L? Shows up in both, count is the same. What about A? It does not show up in this one, so screw it. We only have these two left. This is the max that our result could possibly have. So we've gone through this word and we've gone through this word. Now let's look at this word. Throw it into a hash map and then start comparing. Let's check. Does E show up in both? Yep, and the counts are the same. Does L show up in both? Yep, the counts are the same. So now we've gone through every single word. This is no longer in memory. This is the result. But the only thing we have to do is take this hash map and convert it into a list of characters. I think you probably know how to do that. We're going to iterate over every single key. So we're going to have a loop for that. Let's say every single key in the hash map. And then in this loop itself, we're going to iterate for however many times, let's say I in the range of this quantity, this number. So in this case, it's 1. So we're going to add a single E to the output. And then we're going to iterate 2 times for L. The beautiful thing about Python is that we can actually take a given word and get the count of every single character very easily. We can call counter, let's say on the first word. We're guaranteed that there's going to be at least one word in this list, so we don't have to worry about index out of bounds. So this will return a hash map with the count of every single word. Great. Now we want to go through the rest of the words. What I could do is say I in range from 1 to the length of words, but actually this solution is going to work out the exact same even if we were to iterate over that first word once again, because when we take the intersection of the first word with itself, it's not going to change this hash map at all. That's why it works, and I prefer this because it's more concise, but it really doesn't matter. You can do it the other way if you want to save one iteration. Now, I'm going to take the current word. I'm going to call this current count. I'm just going to call counter on that word as well. So now we have another hash map with a count of every character in that word. Next, I'm going to go through every character. I could actually pick either one. I could pick this one or this one. I'm going to choose this one just because this one is never going out of memory. Like this one is declared out there, and this one we're going to keep reassigning anyway. So I'm going to say for character in count. And I'm going to say, let's get the count of this character in this word, and let's get the count of this character in the other word. And I'm going to take those counts and try to minimize them, and then I'm going to reassign that back to this one. It's possible that maybe this character actually doesn't even exist in the other hash map. In that case, counter is kind of like a default dict. This will evaluate to 0. So in that case, this would end up being set to 0, basically telling us that we don't want any occurrences of this character in the output. So this is pretty much just to get the count of every character that we want in the output. That's what this portion of the code is doing. Now is the time to actually build the result, build that array that we're going to end up returning. So I'm going to go through every key now that's in this hash map. And I
kind of think I understand what's going on now. Equal counter. Oh my gosh, dude. Okay, alright. W in words, we want to check, well, so count is equal to counter W, yeah, for count in cur count if wait for key value and cur count dot items if key if key in count. Count key is equal to the minimum of count key, right? Yeah, and curve count key. I don't need one of the time. Alright, well, for now we want to create a result array. Let's create a res array for key count in we need to make the default value. For key count in items, yeah. Key times count. That was all. What's wrong here? I'm not sure what the bug is here. Oh, we have to iterate from the second word. Is that actually my bug? What is my bug? If we can count, should we count, right? There we go. I don't even think we need to. Okay. That was a tough, easy problem, but I can understand. Curious, how much time does it improve the space complexity when you do this? I'm curious. Not by much. Okay. That was a tough problem. I didn't know there was a counter class like that in Python. Counter class. It's kind of cool. Learn something new every day. Alright guys, well I appreciate you guys watching. Thank you. See you guys later.